Hello, my dear students. Myself, Dr. Amritpal Singh, and I welcome all of you again on this online learning platform. And we are talking about the atomic and molecular spectroscopy. And in our previous lecture, we have discussed in detail about the energy spectrum of Bohr atom, and then we have discussed about the Rydberg atom and how the value of this Rydberg atom it changes with respect to change in the finite nucleus mass. And in this lecture we will discuss how the Bohr's theory it get failed for the hydrogen like atoms, and how the Sommerfeld theory it has given the correction. And actually the Sommerfeld theory says that the size of the nucleus or the shape of the nucleus it is not a spherical in shape, but rather it is in elliptical shape. And then we will discuss in this lecture in detail about the change in size and shape with the change in azimuthal momentum. And then we will discuss about the shortcomings of this Bohr-Sommerfeld theory and how this theory it has been corrected by the vector atom model. So starting our today's lecture, so let us discuss about the failure of Bohr's theory. Now Bohr's theory of hydrogen atom gives the satisfactory explanation for the existence of different spectral lines, and the results of Bohr's theory they are in good agreement with the experimental observation, and they have been calculated for the hydrogen atom particularly. But the Bohr theory it failed to explain the fine structure of atom and the different relative intensity of these spectral lines. And this may be due to the assumptions of Bohr which he has considered while explaining his theory. What Bohr assumed in his theory that the nucleus is stationary. So Bohr's assumption is nucleus is stationary and an electron moves in the circular orbit around the nucleus. And second assumption he has considered while explaining his theory that the mass of electron is negligibly small in comparison to mass of nucleus. So what Bohr has considered that this is the nucleus and the electron which are moving in a circular orbit. So he has given the concept of the electron they are moving in circular orbit, and this theory it has been experimentally correct for the hydrogen atom, but it fails for hydrogen like atoms. Because the Sommerfeld it has found that the fine structure value of a atom it is different for different atomic numbers, and they are no longer spherical in shape while they are elliptical in shape. So Bohr's theory, so failures of Bohr theory. So first failure is it could not explain the fine structure of hydrogen spectral line. And if I talk about the fine structure is the splitting of spectral line into several close distinct components when observed under equipment of high resolutions. So what does it mean that Bohr's energy level in hydrogen atom actually consists of several components which are close to energy. So if I draw here, so what Bohr said that so far a particular orbit, so there is only one energy level, while actually experimentally it has been calculated that there are quite fine structure energy levels, so which are quite close, and the value of these fine structure spectral lines, so their energy levels, energy value, it is different. So Bohr failed to explain these fine structure energy spectrum of hydrogen like atoms. And the second failure of Bohr theory is that it cannot explain the relative intensity of spectral lines. It cannot explain the relative intensity of spectral line. So Bohr said that there is some sort of different energy for different spectral lines, but he did not explain the intensity of that particular energy spectral line. So he did not explain which energy level it is more intense, which energy level which is less intense. So he did not talk about these intensity in his energy spectrum. So third, it could not explain the spectra of two or more electron atom. It could not explain the spectra of two or more electron atom. So he just explained the spectra of hydrogen atom, and he did not talk about those atoms in which there are more electrons which are present in those atoms. So it cannot give detailed fine structure of spectral lines. According to Bohr's theory, the alpha spectral lines of hydrogen, it has a single wavelength that is of the order of 6563 angstrom, but experimentally it is observed that the H alpha line, it consists of two spectral lines, and there is a difference of those small wavelength that is of the order of 1.4 angstrom between these two spectral lines. So the major drawback or the major failure of Bohr is about he did not talk or he did not explain the fine structure of spectral lines. Now the next modification is given by Sommerfeld in 1916. So he explained the fine structure and he modified the Bohr models by assuming that electron could move in elliptical orbit as well. So in addition to Bohr's circular orbit. So he gave the model which is known as the Bohr-Sommerfeld model. So what Sommerfeld said that the electrons, so they are moving in elliptical orbits and along with those circular orbit, and there is change in the quantization energy, and which is changing the position of electron with respect to the position coordinate and with respect to the azimuthal coordinate. So he gave his model. So let me explain, let me draw here. So this is the Sommerfeld assumption. He said that, so this is the positive nucleus which is having a charge plus Zd, and suppose this is the electron which is moving with a velocity v, and this is the radial distance between the electron and nucleus, and the angle that is they are making with those electrons, that is of the order of theta, and this is the direction of its azimuthal angle theta, and they are having some angular motion as well. And from that he explained about the angular momentum of electron. So the displacement of this electron, it has two coordinates, one is r and other is theta, and the momentum coordinates, so that is along with the radial angular momentum, which is given by dr over dt, and the azimuthal momentum number, that is the angular momentum number, so that he explained mr square d theta over dt. And when we taking the contour that is along the 2 pi, so we can integrate this pr dr, that is of the order of nr into h, and similarly for a angular motion that is from 0 to 2 pi, the azimuthal momentum number, that is of the order of kh. So here he has explained two new terms, that is nr, that is known as the radial quantum number, and k, that is known as azimuthal quantum number. So both r and k, they are positive integral values, while pr and p theta, they are known as the radial and angular momenta of an electron. Let us explain. This is our equation number 1, this is equation number 2. So the equation second integral, it is easily evaluated, because according to classical mechanics, the angular momentum p theta of any isolated system, it is constant, and the value of p theta, which varies for integral 0 to 2 pi, so this we can write as kh. So p theta, that is of the order of kh over 2 pi. So here I will write the value of PR. This we can write as R dot. So R dot is dr over dt, and the value of P theta, it is mr square into theta dot. So I will not go in detail about the explanation of the derivation of these two momentum terms, but the Sommerfeld, he comes to a conclusion. So with the derivation, that is b over a, that is of the order of k nr plus k. So here I want to explain. So suppose this is the elliptical orbit. So this is our semi-major axis. So that we generally represent as A. So this is our semi-minor axis, which is represented with B. So the value of this semi-major and semi-minor axis, it is changing as the value of the radial angular momentum nr, and the value of this azimuthal quantum number, it is being changing. So here we can write the term nr plus k, that is of the order of n, that is our total angular quantum number. So this equation becomes for a elliptical orbit, that is k over n, where k, whose value is positive integral, it varies from 1 to n, while n can have any value again from 1 to infinity. So this is the quantum condition for elliptical orbits. So this equation is quite important. So let us write this equation as A. So this equation says the electron can move only in those orbits for which the ratio of the semi-minor to the semi-major axis is the ratio of two integers. So the electron can move only in those orbits for which the ratio of B over A, that is the semi-minor to semi-major ratio of two integers. So from that we can calculate the total energy of electron in a particular allowed orbit and the value of this energy, so that similarly we can calculate from the momentum's value. So the total energy of electron in allowed orbit, so that is the sum of kinetic energy plus potential energy. So here for the Sommerfeld model, the value of this kinetic energy, it is no longer only have the radial velocity, but it also has the angular velocity as well, because the electron they have considered, it is revolving around the nucleus and having some angular velocity that is of the order of d theta over dt. So kinetic energy, so it is sum of radial energy plus angular energy. So this we can write 1 by 2 mv square. So v is dr over dt square, that is the radial component, plus angular velocity, that is equal to r d theta, and the square of this r square d theta over d square. So this is the value of total kinetic energy for the electron which is revolving in the elliptical orbit. So this we can write mdr over dt square plus 1 by 2 mr square d theta over dt square whole square. So similarly the value of potential energy, so that is 1 over 4 pi epsilon of zd square, that is the two charges, one is Zd charge on the nucleus and the E charge that is on the electron, and the difference between these two particles, that is of the order of R. And the calculations which Sommerfeld done for the values, and they have found the total energy expression. So the total energy, that is of the order of minus mz square e raised to power 4 over 8 epsilon naught square h square into 1 over n square. So this energy expression is exactly the same as has been calculated for the Bohr's circular orbit. So this is the energy of electron, which explains that it depends only on the principal quantum number. So this says that the energy of the electron, it is dependent upon the principal quantum number, that is n, and it is independent of the azimuthal quantum number k, independent of azimuthal quantum number k. So next we will derive the value of size and shapes of these orbits and how the shapes it is being changed. And before deriving that, so I want to explain that if the relativistic effects have been considered, so it says that it is independent of the value of k. And next we will talk about the Sommerfeld's fine structure constant. So the Sommerfeld's fine structure constant so the velocity of electron moving in that particular orbit, so that is of the order of v square, that is equal to z square into ma, where the quantity 1 over 4 pi epsilon naught, it has been normalized to unity, that is for simplicity. So the expression of the radius of the orbit in the normalized unit, so the radius of the Bohr radius of an orbit, that is equal to n square h square over 4 pi square me square into z. So from that, when we put the value of this radius here in our velocity equation, so this becomes 2 pi e square over h multiplied by z over n. So comparing this velocity with the velocity of light, so it comes out to be 2 pi e square ch into z over n. So the value of this v over c, that is called the Sommerfeld fine structure constant. And this we generally represent with the term, that is with the term alpha. So let us derive the value of this fine structure constant for Bohr's orbit of hydrogen. Now for Bohr's hydrogen orbit, so where z is 1 and total angular momentum, that is 1, so the alpha, our fine structure constant, its value is 2 pi e square over ch. So putting all these constant values, so alpha, it is coming of the order of 1 over 137. So the fine structure constant is important in the study of the fine structure of hydrogen spectrum. Now here I would like to point out that the value of energy which we have derived, and in that energy value we have derived that the energy, it is only dependent upon the total angular quantum number n, and it is independent of the value of k. And if we taken into consideration the relativistic effect, so if relativistic effects are taken into consideration, the finite motion of the nucleus is considered that the energy of an electron, it is found to depend, so the energy of electron, it is found to depend on both total angular momentum, that is over n, and azimuthal quantum number. So that is equal to k. So Sommerfeld derived the relation of the electron moving in elliptical orbit, and he derived the expression of this relativistic effect and the value of this energy when the electron it is moving with the speed of light or comparable to the speed of light, and the expression of this energy it comes out to be of the order of minus 2 pi square mu e raised to power 4 z square over n square h square 1 plus alpha square z square over n 1 over k minus 3 over 4n. So from this energy value you can see that there are both terms. So this k is the azimuthal quantum number and this n it is the total quantum number. So the value of this energy for relativistic effects it is dependent both on the value of k as well as the value of n. So where mu it is the reduced mass, so the value of alpha it is very small, the contribution to the energy is small due to the azimuthal quantum number, and the effect of this relativistic consideration is to replace the single energy level by several levels with slight difference in energies. So for the allowed transitions, so they have considered the selection rule that is of the order of delta k, that is plus minus 1, and the representation of this energy level for hydrogen atom that is something like this. So suppose this is the ground state, so when n is 1, so for first state here n is 2, so again Sommerfeld said that so there are two values of k, that is for the second orbital energy value at n is equal to 2, and similarly for n is equal to 2 orbital, so he has given three values of k. So this represents the azimuthal quantum number, and the n represents the total principal quantum number. So with the fine spectral lines, so he has given that each orbit it has not only the single energy value, but there are more than one energy values, and the energy difference it is slightly or it is negligibly small. So for Lyman series he has given, so when the electron, that is the first line of hydrogen spectrum, so there are two energy lines, that is from n2 to n1. So similarly for hydrogen beta line, so there are three energy lines. So these all represents the Lyman series. So this is the difference between the Bohr's atomic model and the Sommerfeld atomic model. So Sommerfeld has added that so there are more than one energy levels for a particular principal quantum number. for each principal quantum number, so the shape and the size of that particular orbit, so it is changing with respect to the change in energy. So let us derive how the size and shape of Sommerfeld's elliptical orbit, it changes with change in value of n and k. So we know that the angular momentum number, the azimuthal momentum number, that is equal to kh over 2 pi, and we have derived this relation that the ratio of semi-minor to semi-major axis, that is equal to k over n. So from this, the value of b, that is ak over n, and the value of Bohr's atomic radius for hydrogen atom, its value we know, that is pi m ze square a square over n square h square epsilon naught, or we can write as n square h square epsilon naught over pi m ze square. So this is the relation for the Bohr orbit which we have derived for the Bohr's model. So here we can write this relation as n square over z into a naught. So a naught is our Bohr's radius, so whose value is h square epsilon naught over pi m e square, that is of the order of 0.53 angstrom. So similarly, once we find the value of this a, and we can put the value of this a in this equation, and we can find the value of the semi-minor axis b from this semi-major axis a. So therefore b comes out to be nk over z into a naught. Now we will put these values and draw the elliptical and the shapes of the nuclear orbit for different principal quantum numbers. So this theory predicts that for a given value of principal quantum number n, the value of k, it can have possible n different values. So k, it changes from 1 to n. So this means that for a given n, there are n orbits of different eccentricity, so which can be occupied by that electron. So let us consider the first few cases of hydrogen atom. So for hydrogen atom, so here z is 1. Now first case is for n is equal to 1, we have k is equal to 1. So this we can derive from this relation. So when n is 1, k is 1. So a comes out to be of the order of a naught, and b comes of the order of a naught. So this is our circular orbit. So where the value of semi-major and semi-minor axis, that is coming out to be equal. So that is the radius of Bohr radius of our atom. So this is when n is 1 and when k is 1. So this is our spherical orbit. Now let us take the second case. When n is equal to 2, then we can have k is equal to 2. So for this case, a comes out to be 4a naught and b comes out to be 4a naught, and we can also have k is equal to 1, and in this case a comes out to be 4a naught and b comes out to be 2a naught by putting in the previous equation. So for n is equal to 2, we have a Bohr's circular orbit of radius 4a naught. So this is Bohr radius of 4a naught, and an elliptical orbit with semi-major axis that is of the order of 4a naught and semi-minor axis that is of the order of 2a naught. So for this spherical orbit, so whose both the axis semi-major and semi-minor that is of the order of 4a naught. So this is our spherical orbit and this is our elliptical orbit. So similarly, you can calculate for the total principal quantum number when n is equal to 3. So then there are 3 possible values. So for k is equal to 3, so when n is 3 and k is 3, the value of a, it comes out to be 9a naught, and the value of b, that is semi-minor axis, that is of the order of 9a naught. And similarly, when n is 3 and k is 2, in that case the value of a, that comes out to be 9a naught, and the value of b, it comes out to be 6a naught. And similarly, when n is 3 and k is 1, so the value of semi-major axis, it comes out to be 9a naught, and the value of b, it comes out to be 3a naught. So from that, now we have 3 different energy states. So for a particular energy level, that is n is equal to 3. So first one is when the value of the semi-major and semi-minor axis, it is equal. So that is our spherical orbit. So second is when semi-major axis is 9a naught and semi-minor axis, that is 3a naught, and similarly so this is again the second elliptical orbit where value of semi-minor axis, that is 6a naught, and semi-major is 9a naught. So there are 3 different energy levels. So this is our spherical orbit. So again this is our elliptical orbit, and this is also our elliptical orbit. So we see that corresponding to each value of principal quantum number n, there are n different allowed orbits. So let us say, so if we have three principal quantum number and then there are three different allowed orbits that is present for a particular energy level. So the one is spherical or circular, that is been explained by the original Bohr's theory, while the others are elliptical, all having the same major axis while the different semi-minor axis. So the orbit which is having the lowest k value, so for example in this case, so this is the orbit which is having the lowest k value, so this is the most elliptical orbit. So this is the most elliptical orbit. So this means that the Sommerfeld's introduction of elliptical orbits add no new energy levels. The several orbits, they are characterized by a common value of energy, are said to be degenerate. So all these orbits, so they are having the same energy values. To designate an orbit of given n and k values, the value of n is followed by one of the letters, so that is we represent with S, P, D, F and G. And for example, when n is equal to 3 and k is equal to 1, it is written as the 3s orbital, and when n is 3 and k is 2, and it is written as 3p orbital. And it is seen that the s electron orbit, that is having lowest k value. So lowest k value, it is being designated as the s orbit, and as the value of this k it increases, then it is being moved towards S, P, D, F and G. So this is all about the Bohr-Sommerfeld theory, and there are some shortcomings, so which have not been explained also by this theory, and which has been overcome by the vector form of model, atom model, and that we will discuss in our next lectures. Now what are the shortcomings of Bohr-Sommerfeld theory? So although the theory told how to calculate the energy of the allowed state of an atom and the frequency of radiation emitted or absorbed in transition between allowed state, but it could not tell how to calculate the rate at which such transitions takes place. So it could not tells how to calculate the rate at which such transitions takes place. So it could not explain the variation in intensity of the spectral lines. So it fails to explain the variation in intensity of spectral lines. Second, this theory is applicable only to one electron atoms like hydrogen, hydrogen isotopes, singly ionized helium, doubly ionized lithium, etc.
So this theory is applicable only to one electron atoms like hydrogen atom and hydrogen isotopes like deuteron, singly ionized helium, that is helium plus, doubly ionized lithium, that is helium 2 plus, etc. So it fails when applied to neutral helium atom which has 2 electrons. So it fails for helium atom or for lithium atom which has more than 1 electron. So as we seen, even in hydrogen-like atom, the theory becomes silent on the observed fine structure of spectral lines. So next point is, the theory did not throw any light on the distribution and arrangement of electrons in atom. So the theory did not throw any light or did not explain any point regarding the distribution of and arrangement of electrons in atoms. So how electrons they are arranged in a particular orbit, so this theory failed to explain about that. So the success of the theory in dealing with the effect of a magnetic field on spectral lines was only partial, and it could not explain the autonomous Zeeman effect. So that autonomous and anomalous Zeeman effect, so that how these spectral lines and how the total quantum number, which is not only dependent upon the orbital quantum number but also dependent upon the spin quantum number, and how these orbital quantum number and the spin quantum number, so with the change in this, so there is change in the total quantum number, and due to this total quantum number, so the value of this J, it changed with change in magnetic field. This we will discuss in the Zeeman effect, how the value of this spectral energy lines, so they get changed, so with the change in orbital spin and with the change in orbital quantum number. So this is all about the Sommerfeld Bohr model, and in the next lecture we will discuss about the vector atom model. So hope you have enjoyed this lecture, and if you have any queries you can write in the comment section so that we will check and explain your queries. So till then, goodbye.